Let's look at a slightly different example. A fence 3 feet tall runs parallel to a tall building at a distance of 4 feet from the building. So let's draw a graph first. Suppose this is the ground, and I have a tall building here. And I have a fence that's 3 feet tall, runs parallel to the tall building. So the fence itself, let's say is around here. Okay, and it's 3 feet tall, so this is 3. And it's 4 feet from the building, so this is 4. This is a fence. And they ask you what is the length of the shortest ladder that will reach from the ground over the wall of the building. So I'm gonna have a ladder, so let me change this 3 to the other side. This is 3. Okay, so this is my ladder right here. Okay, we're given this. They ask you to the shortest ladder, so I will need to minimize this part. That's my graph, and now let's introduce variables. So this part, the ladder, let's call it Z. Okay, and you can see that I have a triangle here, right? So if this is Z, I can call this part Y, for example. Then for this triangle, I have this length, I have this length, I have part of this length, so I need this part, so let's call this part X. Alright, once I have that, you can see that, well, I have a triangle here, which I sort of know some of the length, and I also have a triangle here, which I also know some of the length. So maybe I can make use of those two right triangle. And before we start the real question, let's define my variables. So let's say let Y be the height of the building. Z be the length of the ladder. And X be the distance between the bottom of the ladder and the fence. Alright, so now all the variables are defined. I can try to write that as a function of my other variables. So in this case, you can see that we can use Pythagorean theorem. So by Pythagorean theorem, I would have, we have Z square equals to Y squared plus 4 plus X squared. Right? And you can see that this function has two different variables, so I need to use some way to relate X and Y and reduce this formula to one variable only. So to do that, we can use the other triangle we have. So I have this triangle, I also have this triangle, and they're a similar triangle, right? So we can use the properties of similar triangle. Let's write it down. Also, using the similar triangle, we have, so let's see what we have. I have this length over this length should equal to this length over this length. So that's gonna be X over, let's repeat. It should be this length over this length, okay? So X over 4 plus X equals to 3 over Y. So now I can isolate y and plug it back into there. So y would be 3 times 4 plus x over x. Right, so again, let's call this 1, let's call this 2, so I can sub 2 in 1. I have that square equals to, and this looks complicated, I know, 3 times 4 plus x over x, the whole thing square, plus 4 plus x square. Okay, so now we can see that I've reached a formula of z, although it's z squared, but it's okay. A formula of z in terms of only one variable, which is x. In this case, you can see that x has to be greater than 0. Now we can see that although I need to minimize z, but because z squared, my z has to be greater than 0, so minimize z squared can also minimize z. So I don't really need to take the square root or something. I can just differentiate this part, set it be 0, and see where my x is. So let's do that. Z squared prime is gonna be 2 times 3 times 4 plus x over x. Have to use chain rule, so apply times. Here will be quotient rule, x squared at the bottom, and then 3x minus 12 plus 3x. Okay, and then plus 2 times 4 plus x, which equals to, let's simplify it, x cubed at the bottom. So I'm trying to combine those two terms with this term together. Okay, do all of them at the same time, which equals to 2 times 12 plus 3x times 3x minus 12 times 3x plus 3x plus 2x cubed times 4 plus x. Negative 24 times 12 plus 3x plus 8x cubed plus 2x to the power 4 over x cubed. I can open the brackets again and see if I can simplify it. So this part is going to be negative 288 minus 72x plus 8x cubed plus 2x to the power 4 over x cubed, and this can be factored out, and we'll have 2 times x plus 4 times x cubed minus 36 over x cubed. Okay, and now I want this to be 0, so we know that, did I write domain? Yeah, I did write the domain. So we can see that this exists within the domain. And it equals to 0, 1, x cubed, which means x cubed, so x cubed equals to 36. Or x equals to negative 4. Sorry, I don't know why my dog is barking. No, Branny, no. Okay, but this one we have to discard it because, well, we know that x has to be greater than 0, so we can remove it because it's not in the domain. Right, so the only thing we got is actually x equals to cube root of 36. Now, this is my critical point. I need to check if this value would minimize my z square or z, right? So let's try it out. So that's gonna be first derivative test. We can check from 0 to cube root of 36 and so on, z square prime and z square. Alright, so when it's in between 0 and cube root of 36, this is negative, this is positive, so it decrease, increase, which means this is a minimum value. So by first derivative test, know that when x equals to cube root of 36, z square reaches minimum. Minimum, this is the absolute minimum because we have a unique critical point and no endpoint, right? So then that should be minimized at x equals to cube root of 36 as well. Oops. As well, since the square is increasing at z equals to 0. At z is positive, my bad. At z equals to greater than 0. So now you can calculate z. I'm running out of space. Okay, so z square is gonna be this. Plus 4 squared plus the y is gonna be 3 times 4 plus that. 4 plus cube root of 36 over cube root of 36 square, which is approximately 97.33. Of course, you will not be given numbers that's this ugly for your test or exam because you're not a log calculator. But here I didn't try to find a perfect number for you. So take the square root of that, so that is going to be around 9.87 feet. Okay, and that's this question.